Hi guys, welcome back. Today we are going to learn about proving similar triangles. So in this video, what we are going to see are a few different ways we can prove that triangles are similar. Now when we prove something, this is a more drawn out process. So it's not going to be like, oh yeah, I looked at them, they're similar, that's my proof. No, that's not sufficient evidence. It's not sufficient proof. You need strong evidence to back up your claims, and we're going to see how we find that evidence and get into it. So there are three types of similarities we want to start off with. Angle similarity. So this one says if you know two angles inside of a triangle are the same. So here A and D are the same, B and E are the same. Since two of them are the same, the triangles are at least similar. So I don't need the third, C and F, to be equal to prove this because of the fact that the angles in a triangle always had to add up to 180 degrees. If I know what two of them are, the third has to be those two minus 180. So if these are the same, these are the same, by that logic, these two would have to be the same. That's why you only need two of the three angles to make that claim. So if you had two angles, angle, we are done for our proof. The next one is side similarity. You must have all three sides in this scenario. Sides, unfortunately, do not work like the angles because the perimeter does not have to be a set size. So you need to make sure the ratio of all three are the same. So you're going to look DE to AB, see what that ratio is. So let's pretend for this example, this has a ratio of 5. Then if I go BC and EF, I should see a ratio of 5 there. If I go DF and AC, I should again see a ratio of 5. So if they all have the same ratio, that means it's scaled up appropriately. So then we would say it has side similarity. That is a little different than side congruence, which we'll get into later. But we can say they are similar if all sides hold the same ratio. Now there's a way we can combine these ideas. Let's say you only have one pair of angles equal. Well, then we can utilize this, and it's very important where that angle is in relationship. So I need AB and DE to be similar, and I need EF and BC to hold that same ratio. If you notice, angles B and E are between the two sides. So since the angles are between the two sides, what's going to happen is you have those fixed ratios and that fixed angle. There's no way to open this up or close it up a little more in order to make it not similar. The angle in between will fix your ratios properly. If I try and have angle A, I could start playing around with angle A and D, make them the same. I could really play with this angle B and E in between and really make some wild and different results. So we are only going to combine angles and sides in the following way for similarity: side, angle, and then side again. So those are our three basic similarities that we're going to learn about. So let's look at some of them in action. So I'm going to start with an angle and explain why it is. So in this example, I had two triangles here. This is 70 degrees, and this is 33 degrees. And then I got another triangle drawn over here. This is 70 degrees. This again is 33 degrees. Since two of the angles in this picture match up, I have 70 matching with 70. I have 33 matching with 33. This will be similar through angle, angle. And often we'll just use AA for that. Now let's look at some side, side, side similarity. So in this, we're going to see two triangles, and we're going to show that the ratio of all the sides is the same. So this is 6, 12, and 15. This one is smaller actually. I'll draw that a little smaller. Scale really doesn't matter when doing this work, but just for the sake of your visuals, it does help. 4, 8, and 10. So what I'm going to do is pair up the sides, how they match up. I'm going to start with 12 over 8. 12 over 8 will reduce to 3 over 2. Now I'm going to do 15 over 10. (15 over 10) again reduces to 3 over 2. And then finally, 6 over 4 will reduce to, you guessed it, 3 over 2. So since they all have a ratio of 3 to 2 going big to small, that means this is similar by side, side, side. So I can make that claim that these two triangles are similar because all sides hold that important 3 to 2 ratio in this. Now the last example we are going to look at is angle, side, angle. And remember, that angle has to be between the two sides. That's why we say side, then angle, then side again. It's showing us the order to follow. So in this example, we see something like this, and then something like this. So I'm told this angle's 108, this angle's 108. I'm told that this side is 16. This side is 20. I got 20 and 25. So great, right away, I make note that this angle and this angle are congruent. And they are between the two sides. So now what I'm going to do is just make sure, hey, 20 over 16 has the same ratio as 25 over 20. Once I do that, we can start to make a claim of side angle side similarity. So 20 over 16 is equal to, let's see, that reduces to 5/4. And let's see, 25 over 20, it also reduces to 5/4. So there we go. We see that they both had the 5/4 ratio here and here, and the angle in between the sides has to be the one in between them. It can't be one of the ones that's not in between. Has to be in between the two sides, is indeed congruent. So I know this is similar through side, angle, side. So that's a quick rundown of everything. Now let's start to get into a little bit more of the nitty-gritty. We're going to look at an example of something that is close to a side angle side, but see why it's wrong. Then look at some proofs as well. So we'll learn how to write 2-column proofs I got 4 examples with that because I know proofs can be tricky. There's a lot of aspects to them. Kind of want to load you up with examples to look at because it's not, hey, just do the same thing every time. It's, hey, use your brain, use logic, and work your way to the answer. Some proofs may look very similar to each other. Sometimes proofs can look very different from each other, so it's not so systematic. Though there are systematic ways of thinking. So when I look at this, 66, this is 30, this is 30. Then I see one looks pretty similar to it like this. Told that's 44, this is 20 and 20. Now I notice conveniently here, these two sides, 30 over 20 is 3/2, 30 over 20 again is 3/2. So hey, I got 2 sides. These might be similar. However, I don't know anything about the third side. One of these might not fit right. The angles are going to be our giveaway here, though. This angle's 66, where this angle's only 44. Since the angles are different, it's going to throw off that 3:2 ratio of this side to this side. So these are not similar. So they are close to being similar. I would give you that, but I don't care about close. I need to know they're similar or not. And these are not similar. The next thing we're going to do is we're going to start our first proof. This proof is a little faster than some of the other ones we will look at. But, you know, proofs, they take time. They require a lot of brain power. You can't just follow the same systems every time, the same algorithms every single time to do a proof. You have to do a lot of thinking on your own, and you have to try and make guesses on ideas and see if they take you anywhere. So, what we're going to do is I have a picture. It looks something like this. D, E, this is C, A, and B. So I want to prove that the two triangles given are similar. I am going to do that off of the given information. So you're always going to have to be given some sort of information. Oftentimes it will be given to you, or sometimes it will be given to you in the picture. Sometimes it will be written off to the side like it is on this problem. So it says given that DC is perpendicular, or sorry, let me do it in the order they gave them to us. AB is perpendicular to BD. So right away, I know that makes a right angle. We'll get to that inside the proof. And I am also told that E to C is perpendicular to BD as well. So those are perpendicular. Okay. So the first statement we're always going to write in our 2-column proofs is our given information. So I'm going to write here, first column is our statement. And then the second column will be our reason. We can say that. You must give me a reason in these proofs. If you're not given the reason inside the proof, you're not following the purpose of proving something. So when we prove something, you make a statement, you back it up. You make a statement, you back it up. And then you draw a conclusion at the end on the statements that you've already supported. So the first statement here is always going to be super easy. Recopy the given. So AB is perpendicular to BD, and EC is perpendicular to BD. Reason given. That's told to us, so we write that statement as a given. Now we're going to think, what does it mean for things to be perpendicular? Well, that means they make a right angle. So for statement number 2, I'm going to say that DE or DCE, angle DCE is equal to 90 degrees, and the angle DBA is also equal to 90 degrees. And I can say DBA, and I'm allowed to say that because I was already told that things are perpendicular. And by the very definition of things being perpendicular, that means they're 90 degrees. So my reason here is this is the definition of perpendicular. Should I spell that right? So by the very definition of them being perpendicular, that means they're 90 degrees. Well, if two things are both equal to 90, it stands to reason that those things are equal to each other. And that there is called the transitive property. So if two different objects are equal to the same thing, we are allowed to say they are equal to each other through the transitive property. So that is our reason or rationale there. So angle DCE is congruent to angle DBA through the reasoning of the transitive property. Okay, we're almost there. So I know two angles are the same, but I need to grab another angle in there. Well, when I look at this angle D, or as I'm going to call it, ADB and EDC, they're both the same angle, right? Something is always going to be equal to itself. That sounds a little silly to say, like, yes, something's always equal to itself. But it's an important statement to make so we know where that last piece of information is coming from. So here with this, I can say angle EDC is congruent to angle ADB. So I'm allowed to say this is equal to itself through the reflexive property. So the reflexive property seems like a really odd property. Well, something's equal to itself. That's a silly property to have, but it is an important property. So reflexive property allows you to say, hey, this angle is equal to itself. To make our finishing statement, I have this angle and the right angles that match up. So now I can make a statement about my triangle. My finishing statement is going to be triangle D, I'm going to go with the order I put them on our paper. A, B, D is congruent to triangle, now ECD. And how do I know this? I know this by angle. You could just abbreviate that as AA, since we already established that up here, that because I know two angles are congruent, then yes, the triangles are similar through angle. Now you may be saying to yourself, this seems like a lot of work for something that looks obvious. You're right, it may seem like a lot of work, but this is how we prove things. This is how ideas move forward in mathematics. Nobody says, oh yeah, they look the same, let's just go with that. People want evidence, people want proof that they are, and this is providing us not only why we're doing it, but how we're able to do it as well. So the statements and reasons, almost think of it like writing a paper. If you did not include any supporting evidence, if you did not have a conclusion, if you did not have an opening statement, you really didn't write much of a paper. We need an opening statement. What do we know? Then we start making our claims and providing evidence. Then finally, once we've provided our evidence, we write a conclusion. So proofs are very much like a mathematical version of a paper right now. They're a lot shorter to write than a paper because this was a little 5-step proof. Some can be much longer and much more challenging. But for class, we're just going to stick to things that might only be like maybe 6-7 steps at most. There is another way we can do this. I'm just going to quickly go through the explained rationale. I'm not going to write it down. But another proof with this, since these are right angles, due to the fact that we realize that these would be corresponding angles that are congruent, that implies that CE and BA are parallel to each other. And since those are parallel to each other, you could prove that angle DEC is congruent to angle DAB through, again, being corresponding angles cut by a transversal, meaning that you could have said that these two angles and these two angles being the same leads us to that same angle conclusion on our similarity. Definitely a different proof to do. Definitely a little more complex proofs because I had to remember stuff about parallel lines cut by a transversal, but a completely valid proof if I had taken the time to write it down. We got 3 more examples with proofs, and we're going to see what happens here. So we're going to do these as 2-column proofs as well. So the first picture we have is this and this. So this is 9, 18, and 12. This is 4, 3, and 6. SKE and KAW. So when you look at these numbers right away, you may realize quickly that, 3 times 3 is 9, 3 times 4 is 12, and 6 times 18 is 6 times 3 is 18. And you go, well, all our sides have the same ratio, therefore they're similar. That's all we're going to write down in our proof. We're going to take the time to get that all together. Since I had no angles marked, right away I was thinking side, side, side would be the way to go. But we still need to prove it and show that evidence. So the first thing we're going to do, again, we have our statements in one column and reasons in the other. So, first thing I'm going to do is I am literally just going to list out all the side lengths. So I know SK is 9. Oh wait, that's not SK, that's ST. ST is 9, TE is 18, ES, or SC, doesn't matter which way we write, it's 12. Do the same thing for the other triangle. So ST equals 9, TE equals 18, SE equals 12. Then I know KA is equal to 3, AW is equal to 6, and then finally KW is equal to 4. Reason is this is given to us. It's told to us in the picture, so that's our starting point. We're allowed to say that's given. Now I'm going to look at each side ratio individually, and the reason we're doing this is we're looking at side ratios, so that's going to be our rationale. So, for step 2, I'm going to do, say, ST over KA. So that is equal to 9 over 3, which is 3. And this is a side ratio. Okay? Let's do TA, or sorry, not TA, TE to AW. Let's compare those. That's 18 over 6. 18 divided by 6 is 3. So that is, again, a side ratio. Okay. Step 4, let's look at the last remaining side, SE to KW. So that's going to be 12 over 4, which is also 3. So by that rationale, this is another side ratio. So if all 3 sides have the same ratio of 3, we're in luck. So we realize here that these triangles, I'm going to go STE. Actually, what order did I put them in your notes? I just want to be consistent here. Yep, STE. Ooh, almost forgot the little triangle in front to say we're talking about triangles. Triangle STE is indeed similar to triangle that would be KAW. And our reason is simply put side, side, side. So we know all the sides maintain that singular ratio of being 3 times larger in the big one. Since it has a consistent ratio, hey, we know these are similar by side, side, side. So, this one, again, you could have said, well, Isaacoff, it looks like they're similar. Why can't we just say that? You're right, they do look similar. I want the evidence that they are. That's the whole point of this, is for you to be able to find, organize, and present the evidence. So let's look at another example. least little bits in there, but oh well. Okay, the next example has a triangle that looks like this. I got a right triangle here. This is 8. This is 6. And I got another right. Oh, this is a. Nope, sorry. This angle is A. This is S. And this is L. And then I have another triangle that looks something like this. This is M. Sides 4. R. E. So, these look pretty similar. Okay. It looks like because I have an angle in between two sides, I'm going to start trying to prove side, angle, side. So let's just start with our given information. Statement and reason. So again, I'm going to write out everything that's given to me. I know angle A is 90 degrees. I know angle R is 90 degrees. I know A to S is 6. A to L is 8. E to R is 6. And M to R is 4. So angle A equals 90. Angle R equals 90. AL, or I'll do it the way I put it. LA equals 8. Yep. AS equals 6. Then I know RE or ER. Sorry, that was the way I went before. ER is equal to 6. And I finally know that RM is equal to 4. All that information's given to me. What I'm going to do now, since I see it's very obvious that angles A and R are congruent to each other because they are both 90 degrees, let's knock that one out right away using the transitive property. So, angle A is congruent to angle R. That is the transitive property. Now I'm going to start looking at side ratios. I'm going to start with AL, or LA, over, that matches up with ER. So that is 8 over 6, which reduces to 4/3. Rationale, this is a side ratio. Now let's take a look at the next side ratio. That's going to be AS to MR. AS over MR. So AS is 6, MR is 4, so 6 over 4 reduces to 3/2. Okay, my rationale, this is a side ratio. Here's where critical thinking comes in though. Those ratios are not the same. 4/3 is different than 3/2. So in this case, we are unable to prove that these are similar. So we are going to make a statement as a conclusion. So different side ratios means they're not similar. So different side ratios means they are not similar. And you may say to yourself, but hey, look at the picture, they look pretty similar. Why can't I say they're similar? Well, we have evidence that they're not similar. Similar triangles need to hold a consistent ratio. This is not holding a consistent ratio, so I have no right to claim that they are similar. That's what proofs get us. They give us strong evidence. And I have strong evidence here saying that these are not similar. So let's take a look at one more example. And this one, we're only going to have angles in it, so it's going to lead me to believe I'm probably going to want angle as my final statement if indeed they are the same. And we'll see how to handle it, because this one is a little different on its setup. So this one isn't obvious right away. Let me get the darker one. So here with this, I have triangle M, N, E. So this is 72 degrees, and this one's 55 degrees. Then over here, I have something like this, where I'm told that this is 53 degrees, and then this is 55. So that's going to be K, O is in the bottom corner, and P up here. So right away, I'm going to list my given angles. So I know that some angles are given to me, some are not. So I know angle M is equal to 72 degrees. Angle N is 55 degrees. I know angle K is also 55 degrees. So that's going to be a helpful piece of information. And I know the angle where am I? Angle P, sorry. Angle P is equal to 53 degrees. So right now I only have one angle that's the same. Both of them have a missing angle. And I don't know, something's looking like maybe these angles are the same and maybe those are. I'm not sure. That's where our math's going to come into play. So right away, I'm looking at this triangle. What do I know about the angles of a triangle? Well, the angles of a triangle have to add up to 180. That is the triangle sum theorem. Angles of a triangle add up to 180. Theorem's called triangle sum. You know, try and keep it easy for you guys. So I can say 55 plus 72 plus angle E is equal to 180. Our rationale, triangle sum theorem. So, now that I know they add up to 180, I could take away 55, and I could take away 72, right? When I do that, when I start solving this by using subtraction, I get E is equal to 53. So our rationale here is subtraction. And then I notice, wait, if this is now 53, this angle E is 53, well, there we go. E and P will have to be equal to each other. So angle P and angle E are congruent through the transitive property since they're both 53 degrees. Angle E is congruent to angle P. That is the transitive property. And then I can also say the same thing about N and K. Angle N is congruent to angle K, again through the transitive property. Then finally, hey, if I know these angles are congruent and these angles are congruent, hey, I've got two pairs of angles congruent. These triangles are congruent through angle. So I can make one final statement. Triangle M N E is congruent, or no, not congruent,